Hello, welcome to the course PH6B13E Computational Physics. The contents of today's lecture is taken from Numerical Methods for Scientists and Engineers by K. Shankar Rao. We will continue to discuss topics from Module 2, Numerical Methods in Physics. In today's class, let's see how to solve ordinary differential equations numerically. As you know, differential equations or ordinary differential equations, these are the bread and butter of physics, right? Pretty much all physics problems, when formulated mathematically, they get expressed in terms of ordinary differential equations with appropriate initial and boundary conditions, right? For example, the motion of a simple pendulum. This is a simple harmonic motion. And in the case of 1D, you can write the corresponding equation of motion as d square x by dt square plus omega square x equal to 0, where x is the displacement from the equilibrium position and omega is the angular frequency, right? So when you solve this, you get x as a function of time, which in classical mechanics is known as a trajectory. Or if you take electrostatics, you have the Laplace's equation del square V equal to 0. Once again, this is an ordinary differential equation. Similarly, you have other differential equations like the wave equation, del square F is equal to 1 by c square dou square F by dou t square. Or the most famous Schrödinger wave equation. All these are differential equations, right? Okay. So in most of the physics problem, you have to deal with solving differential equations. And some of the equations you can solve analytically, some of the simple equations, but in some other systems, the equations are pretty complex. In such cases, it's manually not possible to get an analytical solution. For example, if you take the Schrödinger wave equation, you can get an analytical solution in the case of a one electron system like hydrogen. But if you take the next complicated system like a two electron system, it's impossible to get the analytical solution. You have to resort to a numerical technique. And luckily for us, there are several numerical methods like Euler's method, Hume's method, Runge-Kutta method, Adams method, etc. to solve differential equation. So a general form of an ordinary differential equation is given by dy by dx. So here x is the dependent variable, and sorry, here y is the dependent variable and x is the independent variable. So dy by dx, which you can write as y prime, this is a function of x and y. Now you cannot solve this differential equation as such. You will require an initial condition. Only then you get the exact solution. Okay. So I am going to specify the solution at a particular point. So I say at x equal to x naught, the value of the solution y equal to y naught. So I write the initial condition as y of x naught equal to y naught. So you can solve this equation and get the exact result only with the help of this initial condition. Okay. And what's your general aim? You want to find the solution function y of x, the value of y for any given value of x. Okay. Let's now talk specifically about Euler's method. So this is one of the simplest method to solve ordinary differential equation, but the downside is that its accuracy is pretty low. Now let's consider the general form of the ordinary differential equation y prime equal to f of xy, and our aim is to find y of x, and we are given the initial condition y of x naught equal to y naught. Okay. Now what we are going to do is we will try to write y of x in terms of y of x naught. How? Using the Taylor series expansion. Okay. So we know how to do this expansion. Y of x equal to y of x naught plus x minus x naught into y prime of x naught plus x minus x naught square by 2 factorial y double prime of x naught all the way to infinity. If x naught is very close to x, then as always all the higher order terms can be eliminated, because if you look at the magnitude, this is going to be much smaller compared to the linear term. So essentially you are left with only the first two terms. So you write y of x equal to y of x naught plus x minus x naught into y prime of x naught. And y prime of x naught is nothing but f of x naught y naught, right? So you can write y of x equal to y of x naught plus x minus x naught into f of x naught y naught. So this is for any general x. Now let's choose a specific value for x. Let me call it as x1, and x1 is very close to x naught, and the difference between x1 and x naught is the increment h, where h is very, very small. So I write x1 equal to x naught plus h. Now y of x1, following this equation, I can write y of x naught plus x1 minus x naught into f of x naught y naught. x1 minus x naught is h, so y of x1 becomes y of x naught plus h into f of x naught y naught. Right? So if you look at what we have done so far, we knew the solution at x equal to x naught. Now using this procedure, you have found out the solution at a neighboring point x equal to x1. So you call it as y1, right? So initially x naught y naught was given. Now you found out x1 y1. Similarly, you can go to next point, next neighboring point x2, and find out the corresponding y value there using the same procedure. So you will find that y of x2 equal to y of x1 plus h into f of x1 y1. So you keep doing this and find the solution at each of the neighboring point. So in general, you can write y of I plus 1 equal to y of I plus h into f of xi comma yi, where xi plus 1 equal to xi plus h. In other words, the new value of y equal to old value of y plus h of xi yi. This is nothing but the derivative y prime, right? And we know that in the context of a function, the derivative is nothing but the slope of the function at that particular point, right? So this is old value of y plus slope into h, which is the step size. So this is the general form of Euler's method. And physically, what's happening? Let's analyze this using a function. So you are given a differential equation dy by dx equal to f of xy, and when you solve it, what do you get? You get y as a function of x, right? So this is what I have plotted here. This is the x-axis, this is the y-axis, and this solid curve is the solution function. Okay, since you are getting the exact solution here, you call it as the analytical solution. Okay, so this line is the analytical solution y of x. And the dotted line, the dotted straight line, is the numerical solution which we get by following the Euler's method. Now here what are we doing actually? So we are given the initial condition, the value of the solution at x equal to x naught is y naught. So x naught y naught point is given. Suppose we want to find the value of y at x equal to x2. Now here straight away we cannot find the solution at the given point. What we have to do is we have to divide our range into small subintervals, and in each subinterval you have to find the solution. So basically you can only move step by step. You cannot directly find the solution. So that's what I have depicted here. I want to find the solution at x2, but I divide it into two subintervals, x0 to x1, x1 to x2. I find the solution at the first subinterval, then using that value I will find the solution in the second subinterval. So it is a step-by-step procedure. Now let's first go to the first subinterval, x0 to x1. So here what I do is I will find the tangent at the point x0 y0. So this is the tangent. So at this point, this dotted line is the tangent, right? And the tangent has a slope which is given by the derivative, and derivative is nothing but f of x naught y naught, right? At this point x naught y naught, the derivative is f of x naught y naught. So basically you're finding out a straight line, a tangent line, which passes through the starting point x naught y naught, and it has a slope f of x naught y naught. Now mathematically, let's see what does it mean. So tangent is nothing but the derivative, right? So tangent at the point x naught y naught, I can write as dy by ds at x naught y naught. And I can expand this as delta y by delta x, and delta y is y minus y naught, delta x is x minus x naught. This is nothing but f of x naught y naught. From this I can write y minus y naught equal to x minus x naught into f of x naught y naught, or y equal to y naught plus x minus x naught into f of x naught y naught. So this is for any general x and y. Specifically for x equal to x1, what is the corresponding y value? You simply put the subscript 1 here, y1 equal to y naught plus x1 minus x naught into f of x naught y naught. And x1 minus x naught is nothing but the step size or the increment h. So that's how you get the Euler's equation y1 equal to y naught plus h into f of x naught y naught. So basically if you look at the first subinterval, you can see that the solid curve is the exact solution, is the analytical solution. Now you are trying to approximate that using a tangent line. In other words, in each subinterval you are trying to approximate a curve using a straight line. So that is the essence of Euler's method. And you know that you can never approximate a curve perfectly using a straight line. That's why at the beginning I said, even though Euler's method is the simplest method, its accuracy is pretty low. One way you can improve the accuracy is by decreasing the step size. We have seen this in the case of trapezoidal method, etc., right? In trapezoidal method also you were trying to approximate the curve using a straight line, and there we have seen that when you decrease the step size, the accuracy level increases. So that's one of the methods you can do. Okay, so in each subinterval you find out the tangent or the slope at the starting point, and using that slope you find out the next y value, right? So here let's look at this geometry. So this is the tangent line. If you call this angle as theta, slope is nothing but tan theta, right? And tan theta is nothing but the opposite side divided by the adjacent side. Or I can write opposite side equal to tan theta, or slope multiplied by the adjacent side. What is the slope? Slope is the derivative, and at this particular point derivative is f of x naught y naught. What is the adjacent side? This is the step size h. So the opposite side of this triangle is given by h into f of x naught y naught. And this point is y1. Up to this point this is y naught. That's why I write y1 equal to y naught plus h into f of x naught y naught. Okay, so this is the idea behind the Euler's method. So in each subinterval you approximate the curve using a straight line or a tangent line. Okay. So using the slope at this point, you found out the solution at this point. Now what you do? You repeat the same procedure. You find the slope or the tangent line at this point, x1, y1. So this is the tangent line. Using the tangent line, you find the solution at the next point. So from f of x1, y1, you will find y. So in each subinterval, you find the solution using the slope at the beginning point. So you keep doing that. So you can see that you are trying to approximate the solution curve using a polygon tree. So that's what you are doing, a polygon tree. Now, as I said, since the accuracy level is pretty low, one of the methods you can improve this is by decreasing the step size. Another approach or a better approach could be, remember here you are finding slope only at the starting point. You can also find the slope at the end point, because the direction of the solution curve in this case is completely dependent on the starting point. So you find solution at this point and this point, take the average of these two slope, and that will give you a much better approximation. So this is what we will be doing in the next class when we discuss about Runge-Kutta method. So in Runge-Kutta method, you are basically calculating slopes at multiple points, whereas in the case of Euler's method, you calculate slope only at a single point. That's the fundamental difference. Let's do a quick problem. Given the differential equation dy by dx equal to 3x square plus 1 with an initial value y equal to 2 when x equal to 1, solve it for x equal to 2 with a step size of 0.25. So the derivative dy by dx or f of xy equal to 3x square plus 1. So even though this is given as a function, a general function of x and y, in our case this is only a function of x, so it doesn't matter. And you are given the initial condition x naught equal to 1 and y naught equal to 2. And step size is 0.25. You basically need to find out what is the value of y when x equal to 2. So let's first draw a table. So x values are with a step size of 0.25, 1, 1.25, 1.5, 1.75, 2. And you are given at x equal to 1, y equal to 2. You need to find at x equal to 2 what is the value of y. As I said, you cannot straight away find out the value of y at x equal to 2. You need to calculate step by step. So first step, find out the value at x equal to 1.25. So y of 1.25, you call it as y1. And from Euler's formula, this is y naught plus h into f of x naught y naught. Y naught is 2 plus h is 0.25 multiplied by f of x naught y naught. Basically in this equation, substitute for x naught. So 3 into x naught square, that is 1 square plus 1. So you get the value 3. So at x equal to 1.5, the value of y is 3. Now using this information, you find what is the value for x equal to 1.5. So we call it as y2. y2 is y1 plus h into f of x1 y1. y1 is 3. 3 plus 0.25 into 3 into x1 square. x1 is 1.25. So 1.25 square plus 1, which is 4.4218. Similarly, you find what is the y value at x equal to 1.75. This is 6.3593. And finally, using that value, you find the value of y at x equal to 2 as 8.9062. So step by step, you find the value. Now you can cross check whether this is correct, because the function is a very simple ordinary differential equation. You can find the analytical solution straight away. So basically, how do you solve a differential equation? So you integrate it, right? This is a first order differential equation. You integrate it once. Okay, so integral of x square is x cubed by 3. So 3 and 3 cancel. Integral of 1 is x. So basically, you have x cubed plus x. Right? Now you can check whether that is correct. When x equal to 1, 1 cube plus 1 is 2. Okay, so you get y equal to 2 when x equal to 1. Similarly, when x equal to 2, 2 cube is 8. 8 plus 1 is 9. So your exact solution is 9, and numerically you get 8.9062, which is very close to 9. That's why we always say numerical solution is an approximate solution. And if you want to improve the accuracy, what you do, instead of a step size of 0.25, probably you can take a step size of 0.1. So in that way you will get a value which is much closer to 9. Finally, let's see how to do this program in Python programming platform. Let's take the same function 3x square plus 1. So first step, define the function. Even though it is a function of only x, we take the general form f of x comma y. So I say z equal to 3x square plus 1, then I return z. Now I need to input certain values. Basically, I need to have the initial value of x and y that will be given in your problem. So I call it as x and y. So I input them simultaneously using the split function. Then I need to get the final value of x at which I want to find the solution. I call it as xf. Then I need to get the step size or increment, call it as h. So if you want, you can input all the 4 parameters at once using the split function, but to avoid crowding, I just wrote it in 2 separately. It's your choice. Then I need to create a table of solution like I did here. So I give the title x value, y value separated by a tab space. So \t gives you a tab space. Okay. Then I need to perform the iteration. For that, I invoke the while loop, and the condition is x less than equal to xf, right? Where xf is the upper limit. Okay. And I print the values of x and y separated by a tab space. So basically, x naught, y naught is readily available here. So first itself, I print x naught, y naught. Now I need to find x1, y1, right? So y1 is nothing but y naught plus h into f of x naught, y naught. So that's what I write here, the equation y equal to y plus h into f of xy. So y1 is calculator. I want to find x1. So x1 is x naught plus h. So I write it here, x equal to x plus h. Y is incremental and x is also incremental. You keep doing this till you reach the upper limit. And after that, you come out of the loop and you simply say print end or print end. So this is a very simple program, and depending on the function at hand, you can modify this part. The remaining part remain pretty much the same. Okay. So when you do this program in computer, you can choose a very small value for h. For example, you can choose something like 0.0001. Okay. So in that way, you can improve the accuracy. Finally, there is an assignment for you. Solve dy by dx equal to x square plus y square at y of 0.8 with a step size of 0.2, given that y of 0 equal to 1. So at x equal to 0, y equal to 1. You need to find at x equal to 0.8 what is the value of y. Choose a step size of 0.8. That's for today. In the next class, we will discuss about Runge-Kutta method. As I said, there we will be calculating slope at multiple points. Thank you.